should be greater than 1 over product of denominators. Yes? Okay. So unimodular intervals are intervals of the following type. So we have interval AB, CD, AB, they're rationals. And the important property that CD minus AB, the distance is the smallest possible with this denominators. So it is the same as AD minus BC is equal. Well, let me write here absolute value. Of course, CD is greater than AB, but let me write it with absolute value because I want to write here plus minus 1. I do not want to think what of the numbers is larger. And what is this? This is a determinant. For those who knows what is determinant, this is 2 by 2 determinant. And this maybe, so this is the definition of unimodular intervals. And now we prove the following lemma, main lemma. Let interval AB, CD be unimodular, then, and alpha belongs to this interval, AB, CD. Then there are 3 opportunities. Either the first endpoint of this interval satisfies this condition. So then either or, this is 1, this is condition 1, or the second endpoint satisfies square root of 5 condition, or what with denominator b, of course, yes, no q. We do not have any q. Here I should write what? D square. Okay, D square. Well, either, look, before formulating this lemma, I would like to introduce one notion. How to add 2 numbers, 2 rational numbers. You should add numerator to numerator and denominator to denominator. It is not good, yes? So we will write here O plus special sign. We work with fractions in such a manner, add numerator. Of course, it is not an addition of fractions, but it admits a very nice property. First of all, this result calls the mediant. Mediant of fractions. A, B, C, D. Then it admits a very nice property. So let us consider the interval. Median always lies between the endpoints. So claim A, B plus CD always between AB and CD. So it is somewhere here. Okay? I think it is obvious. Yes? Well, several secrets. So I will try. You see, I did not finish formulation lemma. I am telling you definitions and secrets. So how to see one of the secrets that although we are dealing with approximation of number by a rational number, so we are interested in real line. Here alpha, we approximate by P over Q. But the people who live on this real line, they indeed are looking for approximation of numbers by another numbers, but they do not see the projective nature of this real line. So they do not know that this real line is embedded in two-dimensional space, and they do not know why. They do not know the reason why this median lies between this. Okay. So secret. So you should. These problems we consider now, approximation of real number by rational numbers, are in fact two-dimensional problems. You should live in R2, and this R, where lives number alpha, and where we approximate it by rational number, is located here in this plane as line x equal 1. So this R1, where we have approximations. Here we have alpha. For instance, we may have here AB. Let us approximate alpha by A over B. What is A over B? It is rational fraction, and A over B, AB, greatest common divisor, is equal to 1. So on this line, there is an integer point with coefficients. So here, what is B, with coordinate B, A. Where is B? Where is A? Is it okay? B here, A here. Yes? Okay. So we do not approximate alpha by rational, as we think if we live on this R1. We approximate one-dimensional subspace which passes through the point 1 alpha. This is one-dimensional subspace. Line. One-dimensional subspace. By this integer point, let us consider point CD. So this is C over D. It means that here I should draw a primitive point. So this is D, this is C. If we consider vector AB and try to add to it vector CD, then the rule is reasonable. A plus C, B plus D. Okay? So there, I should not write O plus. It is natural procedure. But look what happens. We have this vector. We have that vector. We consider the rule of parallelogram to add these two vectors, okay? So here is vector, let it be A plus C, B plus D, yes? And then we take this point, I do not draw here alpha. We take this point and we project it with respect to origin on this line. So x coordinate will be 1. What is y coordinate? Who understands? What? Yes, yes. So this is geometric interpretation why mediant lies between the endpoints. Of course, it is easy to prove by using formulas, but I'm showing you the first. At first, this is geometry. So we have this angle generated by rational integer vectors a, b, c, d. Yes. Inside this angle, we take a point, and if a point is inside this angle, then its projection will be inside this interval. And if we take special point, the sum of these 2 points, then we get that point. So, well, this was a little story devoted to definition of mediant and simple property and geometric interpretation. I am returning back to formulation of my lemma. So, main lemma for Hurwitz theorem says that if we have a unimodular interval, then either one endpoint and alpha inside this interval, then either one endpoint give the necessary approximation, or another endpoint gives the necessary approximation, or mediant fraction gives the necessary approximation what I should write here. You remember that when I was writing at first, I made a typo. I wrote everywhere Q. And you said, no, Q, B and D. Okay. But now, in this third opportunity, what should be in denominator? No? B plus D square. Okay. Okay. So now I will give a proof of this lemma, and then by means of this lemma and by means of something else, we produce an algorithm how to get infinitely many solutions for rational alpha. So proof of lemma. And well, this inequality we call inequality number 1. Next inequality we call inequality number 2. And the last inequality we call number 3. So let us, I don't want to say that we prove from the contrary, but nevertheless we prove from the contrary. Well, okay, assume that 1 and 2 is not valid. Suppose let me draw a picture. So alpha, it is between AB and CD, okay? And both distances are greater or equal than square root. Okay, what I should write? So, what is this distance? This is 1 over BD. It is AB minus CD absolute value. Okay? Because the interval is unimodular. In our assumption, we deal with unimodular interval. Okay, okay. Now we write. So it is greater than sum of two lengths. This length and that length. Okay? Well, we know that neither 1 nor 2 is not true. So we have opposite bounds. So here I write 1 over square root of 5 b square plus 1 over square root of 5 d square. So we have an equality. We forgot this intermediate formula. So this is greater than that. Let us multiply this inequality by d square. So let psi be d over b. Then this inequality turns into psi greater than 1 over square root psi square plus 1. Okay, this is quadratic inequality, which can be rewritten as how we can rewrite this inequality. It is better to write 0 is less than psi plus minus square root 5 psi plus 1. Okay? This is inequality, and this is quadratic inequality. Everybody can solve it. Yes? What is the solution? Oh, I made a terrible thing, but nevertheless, let us. Psi belongs to what? So this inequality is not strict. Then the solution will be a segment. Well, what are the endpoints of this segment? Oh. Okay. Square root 5. Okay. By the way, the segment of length 1. Yes? It's the segment of length 1. But I made, it's a problem. I don't remember. I don't remember exactly the how the proof runs. I don't remember, shall I multiply this inequality by d square, or shall I multiply this inequality by b square? So I don't remember, shall I consider xi or 1 over xi? But we did use a solutions in xi. So what can we say for xi minus 1? To what interval the inverse number belongs? To the same. Okay, let it be I, and xi belongs to the same interval I, because these two numbers in product give 1. Okay, so what we have supposed? We supposed that 1 and 2 both are not true. Okay? But we need to prove that either 1 happens, or 2 happens, or 3 happens. Okay. Well. Let us consider A, B, C, D. And somewhere in between, there is A plus C, B plus D. We need to find an approximation to alpha, one of these 3 opportunities. Well, if alpha is just A plus C by plus D, then there is nothing to prove. Yes? Because the third absolute value, the third difference, is 0. So we have two opportunities then. Either alpha belongs to this segment or to that segment. These opportunities are completely symmetric, so I consider one case. One case from two cases. What case do you prefer to consider? Alpha here or here? Probably here. So alpha belongs AB, A plus C, B plus D. Well, let us write A plus C, B plus D as C prime, D prime. What I want to say? I want to say that this interval is also unimodular. This interval is unimodular also. For those who likes determinants, I can simply write that there is a standard procedure. If we add to one column of determinant another one, it will not change. For those who do not familiar with determinants, we can easily check it. Okay? Well, so we are in the same situation. Our alpha belongs to an unimodular determinant with these endpoints. If we assume, so in the first argument, in the first observation here, we supposed that 1 and 2 are not true. Now here we suppose that 1 and 3 are not true. So because 1 deals with approximation by this point, and 3 deals with approximation by this point, and in our case, alpha belongs to this interval. Well, but we have a conclusion that the ratio of determinants belongs to this interval I. So what ratio? B, I don't know, B over B plus D, or B plus D over B. It doesn't matter. Both of them do. So this is belong to interval. But this B plus D over B is 1. So B plus D over B is 1 plus D over B. It is 1 plus Xi minus 1. Agree? So Xi minus 1 belongs to this interval. We know it from this consideration. Well, but from the consideration of the right-hand side of the blackboard, we know that 1 plus Xi minus 1 belongs to the same interval. Well, what is the contradiction?
How did we show that B over B plus D is in the interval?
Look, what is the argument here? Alpha belongs to an unimodular interval Yes?
Yes.
Then suppose that both inequalities are not true. We have this inequality, and this inequality means that the ratio of denominators of the endpoints psi belongs to, in what order we should take these denominators. What is in numerator, what is in denominator, it doesn't matter. So this situation is the same. Of course, I can repeat all the argument, but I do not need it because we have unimodular interval. Look, simply instead of B, instead of C and D, I can write here primes.
Oh, right. And it's the same interval.
Yes, and everything will be the same. And everything will be the same. So this thing also belongs to the same interval. But psi and 1 plus psi differ by 1. And the length of the interval is 1. So the only opportunity is that psi is psi minus 1 is an endpoint. But psi is rational. It is B over D. And endpoint is irrational. It is square root of 5. So it is not possible. We have a contradiction. This is a contradiction. So these two facts contradict each other. So it means that at least one inequality is valid. We assume that this is not valid, that is not valid, that is not valid, and got a contradiction. Of course, in my argument, I consider one case here when alpha belongs to this interval. But it doesn't matter. For this interval, everything will be the same. So lemma is proved. So we see that if alpha belongs to an unimodular interval, this unimodular interval immediately generates the proper approximation with square root of 5. Now our task is to construct infinitely many such approximations for irrational numbers. For this purpose, we will introduce one more object, which is called Stern-Bracot sequence. Well, what are Stern? Let us consider unit interval. 0. What is 0? 0 is 0 over 1 and 1. What is 1? It is 1 over 1. Now we use the following problem. We have an interval. We have endpoints. This interval is unimodular. And we construct median. Median here will be 1/2. Okay? Now we have, so the initial interval, we call it delta 0. It is a union of two intervals, delta 0, 0, delta 0 is a union, delta 0, 0, delta 0, 1. And delta 0, 1 is 1/2, 1. Both intervals are unimodular. And now I initiate an inductive process. If I have a unimodular interval, I divide this unimodular interval by mediant into two new unimodular intervals, and they will be unimodular intervals of the next level. So I defined a sequence of nested intervals, a family of nested intervals. And also I defined the endpoints. Stern-Bracco sequences are the endpoints of the intervals. So F0, 0 sequence consists of two numbers, 0, 1. And now I'm defining the process. So inductive definition. So if Fn is a sequence, I will write the elements of Fn in increasing order. So Fn is 0. It will be Cn0, then Cn1, then the last element Cn n from n, which is 1. So this sequence of n plus 1 rational numbers. Then I consider neighbors, Cnj, Cnj plus 1, written as irreducible fractions. I consider the medians. So I have a partition. I have a partition of a unit interval. For neighbors, I consider its medians. So the set of all medians I will define as Q n plus 1. Set of medians of neighbors. And U sequence is defined as the old sequence union with new medians. So I explained what is 0 sequence, and I defined inductively having sequence of order n, the next sequence of order n plus 1. So these are Stern-Bracco sequences. One of the home exercises will be yesterday I explained our tradition. I am giving lecture, and then for tutorial I am preparing the sheet with short plan of lecture and a lot of questions, exercises, problems. And one of the problems here will be that this exercise for any PQ rational in 0, 1, there exists mg such as that PQ equals Cng. So in other words, when we proceed with constructing Stern-Bracco sequences, we will obtain all rational numbers in the segment 0, 1. Okay? Well, now let us associate with Stern-Bracco sequence and with partition generated by Stern-Bracco sequence. You see that we have partitions. So this is delta 0, 0 inside some other intervals, So we associate with Stern-Bracco sequences something like slow continued fractions algorithm. One of our next topics will be continued fractions, And then when we discuss continued fraction, then I will ask you how this algorithm which I'm describing now is connected with continued fraction. But nevertheless, look, alpha. What are we interested in? We are interested in Hurwitz's theorem. We should prove something for a rational alpha. Well, so we deal with the rational alpha. But of course, we can work with alpha from the interval 0, 1, because integer part of alpha does not important for approximation by rationals, for the order of approximation. Okay, so alpha belongs to delta 0. Well, it does not equal to median because it is irrational. So we can specify that alpha belongs not only to delta 0, but to delta 0, delta 1, где delta 1 is the first digit in this expansion. It is either 0 or 1, okay? And so on. So if you consider interval delta, which has of level n, which has indices, it is partitioned into two intervals. Delta, the beginning is the same, and the last digit is 0. 0 means that we go to the right. Well, union delta n 1. And alpha belongs, because it is rational, if it be rational, it belongs to two intervals. But if it is irrational, it belongs just to one interval. And it has, so we determine the next code. Should we go to the left or should we go to the right to catch alpha? So finally, we know that alpha belongs to certain interval of level n, and it is more or less clear that the intersection of these intervals, how I can write delta 0, delta, they are nested intervals, delta 0, delta 1, delta 1, delta 0, delta 1, delta 2, and so on. This intersection consists just of one number alpha. Who can explain that the length of delta tends to 0 when n tends to infinity? So in any case, we can choose zeros and ones, but in any case, no matter which is 0 and 1 on each step, the length of the interval tends to 0. Why? The intervals are always unimodular. So the length of the interval delta, which is AB, CD, it is 1 over CD product, yes? And the next interval, it is either AB, C plus A plus C, B plus D, or A plus C, B plus D, CD. In any case, one of the denominators increases at least by 1. So the product here increases, and product is a natural number, yes? The product in denominator increases, the fraction, the length decreases. So product increases by 1, so the length decreases to 0. So all these intervals, any sequence of nested intervals has just one intersection. So now we considered plenty and infinitely many unimodular intervals. For each of them, we can apply lemma. So returning back to our task. Our task is to prove Hurwitz theorem. Hurwitz theorem says that there are infinitely many P over Q, which gives such wonderful approximation to irrational alpha. If alpha is irrational, we have an infinite sequence of intervals, unimodular intervals, which cover alpha. Each interval has endpoints and median. And one of these three rational numbers give the necessary approximation. However, the question is, okay, each interval, each delta gives an approximation. But may it happen that all approximations are the same? So you should ensure that you have infinitely many different approximations. Let us, by the way, up to now, we did not use the assumption that alpha is irrational. So here, when we claim that intervals give different approximations, we should use that alpha is irrational. How we do it? Indeed, let us have a look at the process once more. Where it is the process? Okay, let it be here. Here is the interval. A, B, C, D, okay? And here is median. Alpha is somewhere here. So either this point or this point or this point gives a good approximation. We pass to the next interval. The next interval, look, the first interval we considered have 3 points. The next interval has 3 points, but 2 of them are the same as the points of the interval of the previous level. So it may happen that the next interval does not give a new point. Okay. Let us, so delta, the next will be delta prime. This is larger delta. This is delta prime. Considering delta prime does not ensure that we get a new approximation. Let us consider delta 2 prime, the interval from the next level. It may be this interval or maybe that interval, yes? Considering delta 2 prime also does not give definitely a new, it may give a new interval approximation or may not, because delta 2 prime, there are 2 opportunities for delta 2 prime, this or that, and in both opportunities, the triple of points corresponding to delta 2 prime has a common point with delta without primes. Yes? So it may happen that delta 2 prime also does not give a new point. Let us consider delta 3 prime. Now it is better. Look, for delta 3 prime, there are 4 opportunities. First opportunity, second opportunity, third opportunity, and fourth opportunity. And if we have second opportunity or third opportunity, we definitely have a new approximation, because points here and a new median here definitely different from 3 points with interval delta without primes. For this interval, the situation is the same. We have a new approximation for sure. But we do not know if alpha belongs to these two intervals. Alpha may belong to this interval, and in this case, something terrible happens. Again, delta 3 prime has a point common with delta. And here, delta 3 prime has a point common with median from delta. So the first triple influences on delta 3 prime. We should consider, oh, it's terrible. I do not have enough primes. 4 primes. How? Well, look. But when we consider 4 primes, the situation, in some sense, doesn't become better. Because, look, we consider medians from the right, left, and right, from the very left and the very right intervals. In these intervals, we have n points which coincide with points from delta without primes. But for all other intervals, we have new points. So the terrible situation happens only in the case when we have either very right delta 4 prime or very left delta 4 prime. And if we consider delta many primes, now the situation remains the same. Bad delta many primes, such delta many primes, which still have a common point with the triple generated by delta without primes, are just 2 intervals, the very right and the very left intervals. So the dangerous situation, the case when we did not catch point new approximation at any step, is if we started to choose the very left intervals in our partition or the very right intervals. But if we choose very left intervals or very right intervals, what can we say about this intersection? What is this intersection in this case? Yes, the interval, the length of the intervals tends to 0. Intersection is just 1 point. But all these intervals have this common point, AB. So in this situation, the intersection is A over B. So alpha is rational. Similarly, for this sequence, alpha will be mediant, A plus C over B plus D. But we assumed that alpha is irrational. So it is not possible in our algorithm that eventually we will go to the right only or to the left only. So we used irrationality property and get infinitely many solutions. So one of the exercises, which will be in the list, is as follows. So lemma is theorem is proven. Theorem is proven, and I claim remark, which will be an exercise. So if alpha is square root of 5 plus 1 over 2, then for any epsilon, the following inequality has only finitely many solutions. So this will be exercises. This will be an exercise which we will work on during tutorial. But it is wonderful. We proved a very precise theorem. We proved that this inequality admits infinitely many solutions for any irrational alpha. And not only we are not able to replace this 2 by something better, we are not able to replace square root of 5 by any smaller constant. So from the first point of view, we get an excellent, optimal, and very good result by this method related to partition of the interval into smaller ones by means of taking median. However, this is only impression. If we look further, we will see that this method, although it works here perfectly, in general situations, it is not so perfect. So now I will try to explain you another construction, which from the first point of view does not give such a wonderful result. However, when we look in this new construction once more and deeply, it will be more powerful. So we are coming to Dirichlet construction. Okay, so second approach we will speak about today is Dirichlet theorem. We will prove the following fact, but by another method. Originally, the formulation, let alpha be real irrational, then there exists infinitely many P over Q rationals such that alpha minus P over Q is less than 1 over Q squared. So you will say, what about it? How to prove this theorem? It is a corollary of that. It is not good. It is not good. So, because for our purpose, not the result itself, not this result in himself, itself is of interest, but the method how we prove it. Moreover, we will prove this will not be the main result. This will be a corollary of another result, a corollary of what we call global result. So this is Dirichlet. Well, Dirichlet formulated it as a theorem, but in fact it is not a theorem. It is a corollary of a so-called global theorem. I will formulate this global theorem in 2 versions. The first version is as follows. So for the global theorem, what is global theorem? For any alpha real, we do not assume that alpha is irrational. And for any q positive integer, there exists q positive integer such that two things are valid. First, that alpha minus p over q is less than 1 q in denominator. And the second is that q small is less than q capital. You see, this formulation is a little bit complicated, and we do not see what does it mean at the very beginning. However, we can easily understand so that from global theorem, Dirichlet's theorem follows. So I will explain it right now. Why global theorem follows from Dirichlet's theorem? First of all, if q small is less than q capital, then alpha minus p over q is less than 1 q less than q square. Okay? So at least one solution really follows from Dirichlet. To get infinitely many solutions, we should use additional assumption. Look, in global theorem, there is no assumption about irrationality. So to obtain infinitely many, we need irrationality. So if alpha is irrational, this is not 0. Okay? This is not 0. Then it means that we can take q1 such as 1 over q1 is less than alpha minus p over q. And then for q1, by the same theorem, we catch q1 small such that and we get another approximation, which is also non-zero, and so on and so on. We get infinitely many approximations. By the way, Dirichlet theorem, global Dirichlet theorem, may be reformulated in the following way. Reformulation of global theorem. For this reformulation, I need the following notation. So by this, I will denote distance to the nearest integer. Distance the nearest integer. Global theorem may be formulated as follows. When alpha is real and q is positive integer, then minimum distance to the nearest integer q alpha for q less than q is less than q minus 1. So this is a very compact formulation which has a certain sense. It is related to so-called irrationality measure function. We will discuss it a little bit later. So how we can compare the poverty of methods, I mean method, Gurwitz method, Stern-Bracco method, and Farinet method, and Dirichlet method, irrationality measure function method. I will explain you later. So now I shall prove global theorem. Well, Gurwitz theorem, I will prove it here. Proof of global theorem. proof of global theorem. Well, okay, Dirichlet means pigeonhole principle. So we consider fractional parts alpha x, where x is equal 0, 1, 2, up to q. So all these fractional parts belong to the interval 0, 1, okay? It is, so these are pigeons. What are holes? So interval, we divide into segments, half open segments. Well, we have q plus 1 pigeons. And how many holes? How many holes we have here? How many intervals, smaller intervals? Q. Q holes. Q holes. What does it mean? It means that there are two pigeons in one hole. Well, so there exists x greater than y such that alpha x fractional part and alpha y fractional part belong to the same interval. The length of the interval is 1 over q. So alpha x minus alpha y is less than 1 over q, okay? It's less than 1 over q. What does it mean? What means fractional part? Fractional part is number itself minus integer part. So we conclude that alpha x minus alpha y minus certain p is less than 1 over q. Now we write q x minus y, as x was greater than y, q is greater than 0, but it is less than q because maximal x is q capital and minimal y is 0. And we have alpha q minus p is less than 1 over q. So this is the approximation statement. Being divided by q small, we get this. Well, and being and considering this, we immediately get 2, because here we just say that q is positive and less than q capital. So by pigeonhole principle, we proved everything. So now I should turn. Well. What I can say next? Okay, I will give an interpretation of this theorem in terms of our two-dimensional plane. So geometrical interpretation. Here is x, here is y. Here is line y equal alpha x. First of all, interpretation of Dirichlet theorem. Look, where we catch integer points, we consider hyperbolas y equal alpha x plus minus 1 over square root of 5x. And we catch, so I can rewrite this. Well, how I can rewrite this? Q alpha minus p is less than 1 over square root 5q. What is q alpha minus p? Look here. If I have an integer point, q p, this segment from this integer point to the corresponding point on the line y equal alpha x is just q alpha minus p in absolute value. So Hurwitz's theorem says that if we consider these two hyperbolas, and if we consider the following domain, infinite domain, around the line y equal alpha x, then there are infinitely many integer points in this domain. While global Dirichlet theorem says, why, now I'm explaining the word global, why we call Dirichlet this theorem global and this theorem local. This theorem says that there exist infinitely many points. We do not claim where they do exist, just infinitely many points, somewhere. But Dirichlet theorem in global form says something different. It says that if we consider this y equal alpha x, and we consider arbitrary q, and we consider this point, this vertical line, we consider here 1 over q, and we consider parallelogram which facet has length 2 over q, and another side is parallel to y equal alpha x. And Dirichlet says, global theorem says that for any q, this parallelogram contains an integer point. This is the difference. Global means that you can take any q and you will catch integer point. And Hurwitz's theorem says that there are special points which gives better approximations, but they may be not very often. And in global setting, Dirichlet theorem is also optimal. It is not possible to replace this 1 here. Here, what is q minus 1? This is 1 over q. So 1 is a constant. It is not possible to replace this constant by 1 minus epsilon in global setting in such a way that the result will remain valid for all q's. So this constant 1 in such sense is also optimal. So Dirichlet and Hurwitz, there are two different approaches, local approach and global approach. Okay, so now I want to compare multidimensional opportunities of Hurwitz and Dirichlet. But I am not sure that I have enough time. How much time is left? 20 minutes. Oh, excellent. Excellent. So I will tell you briefly something about multidimensional approaches. Okay. because I want to speak about multidimensional approach, and I want to connect it to our previous exercises, to Liouville theorem in its more or less general form. Okay, so Hurwitz. Multidimensional version. It's a pity. So I think I will speak about two-dimensional approach, because in Hurwitz multidimensional approach has some complicated combinatorics, but well, what was essential for Hurwitz? We take a partition of interval, we divide this partition, we take unimodular partition, and we have a process of dividing this partition and getting something. Well, it is possible to have a similar multidimensional generalization. Look, by the way, what is rational point? So, if we consider a rational number, then real rational number, then it can be simply written as a ratio of two integers, integer over positive integer, and we should, for uniqueness, we should assume the deca prime. If what is, so now this is in R1, which is rational point you may remember this picture which I draw in the very beginning. So here is rational point P over Q, but in fact it is a projection of a primitive integer point. Yes, QP equal 1. Okay, if we have, so AB, this is rational. We are interested now in a representation of rational points in R2. What is rational point? So if something, let it be, so Z is rational, it means that Z is equal Z1, Z2, where Z1 and Z2 are both rational numbers. How do you think? What is a canonical way of representation of a rational point in two-dimensional plane? So a rational point in one-dimensional plane, rational number, canonically it is numerator over denominator, two coprime numbers, denominator is positive integer. What is, in your opinion, the canonical representation of a pair of rational numbers of a rational point in Q2? How can we represent it as a fraction? Look here, look here. We have 1x and 2y's. If we are interested in approximation in R2, we should understand that this R2 is embedded in R3. So here is R2, which corresponds to plane x equal 1, and it is embedded in R3. And people who live in this R2, two-dimensional people, they see these rational points. They investigate these rational points, but they do not know that these rational points are obtained as a projection of primitive integer points. So in fact, there is an integer point with coordinates q in x and coordinates p1, p2 in y's, and integer point, rational point here in two-dimensional space is a projection of a primitive. What does mean primitive point? Primitive means that great common divisor is equal to 1. So I'm repeating the question. So if we have a rational point, what is how we should define its canonical representation? Yes. We need to write Z1 is equal P1 over Q, Z2 is equal P2 over Q, and condition for uniqueness that this GCD is equal to 1. Okay, so a canonical representation of an integer point is as follows. Well, now I am trying to explain how we generalize Stern-Bracot. The picture with Stern-Bracot did not survive, so we have an interval, and to construct the next interval, we consider mediant, yes? And instead of the interval, we consider two next intervals, which are generated by partition by this median. We started with unimodular interval. Unimodular interval, what it means in our two-dimensional interpretation? It means that we started with vector 0, 1 and 0, 1, 1. Maybe it should be more reasonable to start with 0, 1 and 1, 0. So start with vector 0, 1 and 1, 0, infinity. But it doesn't matter. So in any case, we started with it. We took a basis of an integer lattice and divide this basis of an integer lattice into two sub-bases and continue the process. So now we should do the same in three-dimensional case. We start with basis of an three-dimensional lattice. For instance, what basis we can take? Unit vector this, vector this vector 0, 0, 1, 0, 0, this vector 1, 1, 0, and this vector 1, 0, 1. And continue the process. So for people who live, so this Stern-Bracot partition was explained in terms of people who live on one-dimensional line and who do not know the line is embedded. So I can explain also this partition. So okay, R2. Let us work with triangle. Let us work with triangle. We are interested in approximation two-dimensional vectors in this triangle. Let this triangle be T0. T0. Triangle T0 is triangle with vertices 0, 0, 1, 0, 0, 1. Okay? Now, analogously to Stern-Bracot, we define a partition of this triangle into two triangles. So we have, let 0, 0 be point, we call it A0. This point we will call A minus 1. And this point we will call A minus 2. I don't remember well what point should be. Well, it is important that A0 is 0, 0. And I want to define the next point. The next point I defined as follows. So this point, we do not use this point. We consider two previous points. By our procedure, this is a rational point. It is written as A, B over C. Well, this point is written, let it be A prime, B prime over C prime. Okay? And now I consider a mediant. What is mediant? A plus A prime, B plus B prime over C plus C prime over C plus C prime. This point will be somewhere inside this segment. So if we consider 0, 1, and 1, 0, this will be point just 1 half, 1 half. I am speaking about, on this picture, I am explaining a general step. Then I divide this triangle into two triangles by considering this edge. So, and this will be A1. Now, instead of one triangle, I have two triangles. I have two triangles. And the last, so the last point, so in the initial triangle, the last point was A0. In two new triangles, the last point is A1. So what I do next, I am taking the last point, consider the opposite edge. Opposite edge has rational endpoints. I write these rational endpoints in such a representation. I calculate median and divide each of triangles into two triangles. And in each of new triangles, I have a new point, and I continue the procedure. In such a way, I construct a division of triangle into smaller triangles. This division, this is called Monkey-Meyer algorithm. By the way, Monkey-Meyer algorithm was invented by the same Hurwitz. In the same paper where he explained this proof of the theorem which I told you, at the last page, he explains this algorithm, but it is not clear that he explained this algorithm there because he does not use formulas and he writes it by words, of course in German. Well, but nevertheless, that's why they call it Monkey-Meyer algorithm, because nobody read Hurwitz. But Hurwitz invented it. So what is very good? Very good that it's a straightforward generalization, and you can prove something. One of the exercises, one of the home exercises which we'll work on, will be to prove that during the Stern-Bracot procedure, we will obtain all rational points in the interval 0, 1. Here, by means of this procedure, we also obtain all rational points in the interval in the triangle 0, 0, 1, 0, 0, 1. This is an easy exercise. I hope I was very impressed by yesterday because you solve a lot of exercises. Some of them are not so easy. So I hope this will be solved today. What we proved during the lecture, we proved that for any choice of deltas, delta 1, delta 2, delta 3, the sequence of corresponding nested segments converges to one point. You may remember why we proved it arithmetically, because the length tends to 0 because each time one of the denominators increases at least by 1. Here, in Montgomery algorithm, the situation is the same. If we consider a sequence of nested triangle, it converges to a single point. However, it is not possible to prove this by means of area, because area may become smaller, smaller, and smaller, and nevertheless, so the proof of this fact is more or less complicated geometrical problem, which may be not easy. So it is a not easy exercise. Further, Gurwitz in dimension 1 gave a brilliant result that every number, every rational number admits such approximation. This algorithm, although it converges to every point, gives no quantitative bound at all. And it is possible to formulate a corresponding statement. And I think, although it should not be extremely difficult, I think it has never been documented. So it is one of a simple, maybe open problems. It was not documented because it does not give reasonable approximation. However, the second approach, which we work on today, Dirichlet approach, really gives a reasonable approximation. So I will say few words about multidimensional Dirichlet approach. How much time do I have? At least 20 minutes? 4 minutes. Okay, well, okay. Let me formulate the simplest statement from Dirichlet. Dirichlet, global Dirichlet in dimension 2. Global for simultaneous simultaneous, I will write simultaneous approximations. Well, what is simultaneous approximations? We have several numbers. I will speak about arbitrary dimension because Hurwitz generalization to higher dimension admits complicated combinatorics. In dimension 2, you do not see this combinatorics, just triangles. But in higher dimension, the combinatorics, look, there is combinatorics, some, you see, what is, the last is A0. The previous is either this or that, 2 opportunities. But in higher dimension, the order is of importance, and you should take care of order. It's complicated. We will not speak about it. In Dirichlet, there is no order. I will formulate a global theorem. So alpha 1, alpha n is a real number, is a real vector. Well, we are interested in making small simultaneously approximations to all n numbers, to all n coordinates of the vectors with the same denominator. We are taking minimum over q less than q capital and this is less than q minus 1. So there is a mistake in this formulation. Let us try to check intuition. So one symbol in this formulation is omitted. We will speak about multidimensional versions during tutorial and during next lecture, but maybe somebody has intuition to correct the statement. So it is an n-dimensional statement. Something here is omitted. For n equal 1, we put here n equal 1. It is a formulation which we had 20 minutes ago. Well, does anybody understand? But it is, you should have intuition. You may improve the situation. So if you change here, it can be improved here, but here you need two symbols. If you deal with another place, you need one symbol. Okay, here we can put n. Either here we leave n and here put 1 over n. I prefer this because this is one symbol instead of two. The sense of this theorem is as follows. We consider R n plus 1. This is x. This is y1, yn. We consider line. Line in n plus 1 space is determined by n equations. Y1 is equal alpha 1x, and so on. Yn is equal alpha nx. If you are afraid of higher dimensional space, please think that n equal 2. Then it is natural stereometry. And what do you have? We have here q. We have here point on the plane x equal q. We surround this point of a plane by a square, by a hypercube with edge 2 over q. And we shift this cube along the line y equal alpha x and catch integer point in such a parallelepiped. Simply speaking, the volume of this parallelepiped is 2 to the power n. Because the volume of the cube is 2q to the power n plus 1, and the height is q. So q, q, no. I have forgotten to write here qn again. I made a mistake here because I wanted to ask you to correct it. And here I forgot to write. So here q to the n, because minimum for q less than q to the n. So then here will be n-dimensional space. So the length of the edge is 2 over n. 2 over n to n is the volume, n-dimensional volume of this box, multiplied by the height, which is qn. We have 2 to n. And who knows Minkowski-convex body theorem will understand that catching an integer point here by Box principle, by Dirichlet principle, is the same as catching by Minkowski body theorem. We will speak about Minkowski body theorem a little bit later. So this is an advertisement of some future lectures. Okay, I think now we will have a break, and you are very welcome to our